No.
So switch on my video, or I can continue with just.
Sukhendu, you are not audible. Hello? Yeah, yes.
Is it?
Yeah, it's fine now.
Hello. Is it clear now?
Yes, Sukhendu.
Okay. So, Dilpreet, just tell me one thing. So, all the time I should keep the video on, or I can just stop it.
You can switch on your video. It's no problem.
Okay. So let me share my slide first. So my screen is visible.
Yes, Sukhendu, it's visible.
Okay. So now, what about slides now?
Yes.
Is it visible? Slides?
Yes, Sukhendu, it's visible.
Okay. Okay. And the size of the slide is fine, or shall I put in full screen mode?
You can put it in full screen mode. That will be.
Yeah. Okay. Okay. So I'm going to discuss about application of eigenvalues and eigenvector in differential equation. And so in the title, I have not mentioned directly differential equation because uh, not only in differential equation, in advanced level, it is applicable to actually hydrodynamic stability theory. So in this talk, I am going to discuss about more advanced thing where you can apply this eigenvalue and eigenvector concept. Okay, so obviously to handle that advanced problem, you need the idea of differential equation. And so at the end, actually you are working with differential equation and you are applying linear algebra on the differential equation to solve some advanced problem and real life problem. Okay, so in the first talk, I'll discuss about the applications, how to design the application, how to model the application by help of differential equation. And then in next session, we can talk about how to solve those differential equation using eigenvalue, eigenvector, or what is the use of eigenvalue, eigenvector in the case of a differential equation as well as a practical problem. Okay, so once I finish the first talk, then even we can discuss in details if you have any kind of queries. And similarly, after the second talk also, we can discuss about the details if you have any kind of queries. Okay, so let me start with introduction about the applications and as well as where we can use this kind of theory, eigenvalue, eigenvector theory, and where we can use this hydrodynamic stability theory. Actually, to solve hydrodynamic stability differential equation as well as the knowledge of linear algebra. Okay, so actually in reality, you know there are various type of flow system. So hydrodynamic stability theory actually tells us about the various state of a flow system as well as if you have a flow system which is disturbed by some outsourced disturbance as well as say some other disturbance then that state of the fluid can be changed. And now our aim is to study if there is a equilibrium system or initial system, and if you are disturbing the system, then after certain time or after certain position, that system again coming back to the previous state or previous position or not. Okay, so I am starting with a very basic actually real life application. That is, if you see figure 1, this is nothing but a tap water. So in our daily life use, always we are using the tap water, and I have given 3 different figures for tap water. In first case, you can see that water is coming slowly. That means at the initial stage, when you have just opened the tap, pressure is less and water is coming from the tap, and therefore the flow is somewhat parallel kind of thing. In the flow of the water is parallel here. So this kind of state called equilibrium state or initial state. Now, if you go to the second figure, sorry. So second figure, you can see that here fluid pressure is somewhat increased, and therefore your flow system has changed. And now you can see the trajectories inside the flow system are disturbed. They are no longer parallel, and this kind of thing or this stage is called something called Patav state. And last one is, if you can increase the fluid pressure, if the fluid pressure is very high, in that case you can see fluid is not following any kind of particular path. So one kind of chaos started inside the system, and therefore the streamlines are completely broken. They are neither parallel or not following any kind of geometry. Okay, so from this figure it is clear that in our real life application there are certain kind of flows where you can see that different kind of stage of the flow system. First one is equilibrium stage or initial stage. Second one is Patav stage or disturbed stage. And third one is turbulent stage. So to controlling the turbulent stage is very difficult. And therefore, we have to study the Patav state, and we have to check for stability of the Patav state. That means after giving some disturbance in the system, that system is completely destroying, or that is completely disturbed, or the system D can coming back to system A. That means equilibrium state. Okay, if it can come back to it can come back to the stage 1 or stage A, then you can tell the system is stable. But if it is not coming back to stage A, rather it is going to stage C, then you can tell that system is completely unstable. So this is somewhat a basic idea about the hydrodynamic stability theory. Okay, so and I have given one example, real life example, where you can see that this theory has a use. And similarly, I have given another biomedical example here. So it is something human blood flow, and there also you can see this is nothing but this blood flow is nothing but one kind of hydrodynamic instability mechanism they are following. So and you know that in the case of blood flow, depending on the situation, this instability, if there is an instability, that means if the system is completely destroying or it is going some stage where you cannot control, so that kind of system called turbulent system. And this unstable system sometimes has bad impact in our life, like heart attack. You know the heart attack, that is the bad impact of hydrodynamic instability. On the other hand, so when in the case of drug delivery, say you are suffering from a disease and you have taken a drug or injection, then that injection or drug will slowly reach to your reach to the appropriate position due to the hydrodynamic instability inside the blood flow. Okay, so these are somewhat the application of hydrodynamic stability theory, and there are many more examples where you can see hydrodynamic stability, and that can be modeled using certain differential equation. And once you can model the system with certain differential equation, you can use the idea of linear algebra there to solve the system. Okay, so first of all, slowly I will show you how to model this kind of various kind of system, flow system, and then I'll show you how to solve a model problem, a model differential equation using eigenvalue, eigenvector knowledge. And later on, I will show you how to solve a complex system using eigenvalue, eigenvector, and what are the use of eigenvalue, eigenvector in this kind of system. So next thing is actually, let me tell little bit more about this complex system. So complex flow or complex systems are nothing but a system inside which many things are changing with respect to position as well as time, etc. So if you can think some complicated flows like tear film flow inside the nozzle, so which is very important nowadays, and there are many more actually industrial application where you can find out many complicated flows. Okay, that means inside the system, complicated flows or complicated system is nothing but inside the system properties are changing frequently with respect to time as well as space. So in that kind of system, since properties are changing, handling the system is very difficult. Okay, so you have to model the system in a appropriate model such that you can handle the complex system, as well as once you model, if you are looking for the solution of the system, you have to apply appropriate analytical or numerical method. Okay, so in this talk, I'll discuss how to use eigenvalue eigenvector method to solve such complex system or complex flows. Okay, so here are some more examples of complex system I have given. Say you have some bounded system. Okay, bounded system means it has some boundary. Okay, so if there is some boundary and you are considering a complex flow system or complex system, that means inside that boundaries there are two or more materials or things are there and their properties are different. Okay, so if you see first figure, you can see that I have taken the example of flow system as a complex system, and here I have taken flow of two different materials or two different fluid, and therefore you can see that there is a change in properties which is given, which is representing by this dotted line. In fluid 1, properties is following some constant rate. In fluid 2, properties are following some other rate, and therefore between them there is a difference or jump in the properties, and that kind of property jump we can represent by a step function. Okay, so in the first case, any property jump between two different things can be represented by a step kind of function. In second case, you can see I have taken two dotted line. One is linear function and another is non-linear function. You can find out such kind of materials or such kind of applications where properties are either changing linearly from one wall to another wall or one boundary to another boundary, or you can find out that some other material or application where properties can change non-linearly. So that can be represented by a non-linear function or a linear function. Okay, as per your application, as per your need. Similarly, properties can change with another different actually smooth function. So say in first part or first material it is constant, in second material also constant, but in between there is some material or some type of flow where it is changing continuously. So in that case we can take a smooth function, continuously differentiable function, to represent the properties of such kind of application or such kind of system. Okay, so in reality whatever application we can see or we can look for, everywhere there is mathematics, and everywhere you need the knowledge of mathematical function as well as the various theory of mathematics. Okay, so now let me tell about how to model such kind of system, how to model the disturbance of a system, and if a system is disturbed, how to actually control the disturbance inside the system. Okay, so at the beginning I told a system can be unstable after giving certain disturbance or certain if you change some internal things, due to that it may become unstable. That means it will move from equilibrium state to one perturbed state, and then if perturbation grows, then completely it will become unstable. Okay, so graphically I have denoted here various kind of things. So first one, say there is an object. Okay, so circular object. I am thinking that this is your material, this is your application, or you want to model this object and you want to check the instability or stability with respect to perturbation of this object. So you can see that depending on its position or some other properties, it can be stable if the situation is such that after applying small perturbation, there is no much change in the position. Okay, so in this case, first case, in the first figure, you can see that if you disturb this object little bit, then actually what will happen? Nothing will happen. It will come back to its original position if you are giving a small disturbance. So such kind of system is called stable system. But if you consider the next figure, you can see here the position of the object is such that if you can disturb little bit, whatever small disturbance you give, the position of that object will be different. It will go somewhere else. Therefore, this kind of system is called unstable system. Okay. Whereas if you say third case, you can see that in this case, if you apply very small disturbance to the object, nothing will happen. Okay, it may come back to the original position again, and it will not be displaced much more. And so this kind of system called neutral system. That means your perturbation has no much effect in your system. And last one is called conditionally stable. From the name itself, you can guess the definition. So conditionally stable means, say in this case, if you give small disturbance to the object, what will happen? That object will come back to its original position after a certain time. Okay, but if your disturbance magnitude is high enough, okay, it can go away. It can go away if your perturbations or disturbances are high enough. Okay, therefore in this case the situation you can tell that conditionally stable. That means you have to restrict your perturbation range in such a way that the solution will not grow up, and therefore the system will not be completely destroyed. And so this kind of system is called conditionally stable. So I have tried to give some graphical actually presentation of various kind of nature of a object. Okay. So next thing is how to model this phenomena. Okay. To model any kind of physical phenomena, you need a differential equation. Okay. So now So say we have a very simple actually object or very simple physical phenomena and we want to model it. So then we can use a very simple dynamical system. Okay, that means a set of first order differential equation or a single first order differential equation. So at the beginning, I am starting with a very simple differential equation and say this differential equation is modeling certain phenomena or certain properties or certain change in a application, and therefore this equation gives the behavior of the object. Okay, now behavior of the object depends not only time, also on space or certain more parameters. Okay, because in a system, space-time is present, but there can be some other controlling factor which can control the whole system. Okay, so such a control parameter here is RE. Okay, I have taken this parameter because in this system, say there is time, there is space. Basically, this system is only time dependent. There is no space. Okay, space dependency. But I have introduced one control parameter that is anything that can manage some properties of the system. And so this differential equation actually tells us about how the property Q is changing with respect to time. And that is given by the function f of Q into R, Q comma R. Okay. So in this case, it is noticed that the equation is dependent on time. That means the property Q or the function Q is dependent on time. So autonomous in time. It is autonomous in time. Therefore, if you are interested in finding the initial solution of this system or equilibrium solution, that means the first stage, you want to solve for the first stage. Okay. In that case, what you have to do at the initial stage or equilibrium stage, we know that the properties are somewhat constant and they are independent of time. Okay. So in that case, when you are considering a equilibrium solution, obviously we can tell that the time derivative of the function Q is 0. And so equilibrium solution is nothing but given by f of qb comma re equals to 0, because dq by dt is 0 here whenever you are finding a equilibrium solution. So here actually I have denoted the solution, equilibrium solution, by qb. Okay, so this is nothing but your initial stage or equilibrium stage. So in this stage there is much variation in the properties, and so properties are constant with respect to time, and we found the solution, equilibrium solution for this system. Okay, this can be applied to any system. If you are taking any differential equation to model a system, this approach can be applicable to find out a equilibrium solution. Okay, now as I told, there is a control parameter. Okay, there is a control parameter or say parameter inside this system which is controlling the growth, decay or change of properties inside the system, that is RE. Therefore, this equilibrium solution may behave differently in different range of control parameters. Okay, so that's why I have given a graphical representation of solution behavior. You can always find out a branch cut or a boundary, lower boundary as well as upper boundary, where this solution can be completely stable or conditionally stable, and you can find out some other range of control parameter which is RE. For that, it can be unconditionally unstable. Okay. So therefore, since this is a control parameter, depending on the values of RE, the behavior of the solution may change, and so you can find out different region where solution behavior will be different. Okay. So next thing what I told, this solution is equilibrium solution, and therefore next thing is as I mentioned at the beginning, next thing is we want to introduce a small perturbation in the system. Okay, we had a differential equation. Now we have a equilibrium solution or initial solution. But that solution is not valid always, because equilibrium solution is valid only on the initial stage where no change in properties take place in the initial stage. Therefore, equilibrium solution is valid only on the initial stage. Now, in the later stage, your solution will change, and say you are correcting the solution introducing a perturbation. Okay, you have something equilibrium solution, and then you are changing the solution behavior using the perturbation or a correction. Okay, you are adding something or subtracting something from the solution to get the original solution. Then in that case, if you are introducing a perturbation, so this is not similar like your Taylor series expansion. You know the value at a point and you want to find out the value in different point. That means you have to correct the value of the known point by using some other terms. Okay, same thing here. You have a system that initially that was in equilibrium state. Now there, due to some outsource or in-source disturbance, it is disturbed. So my solution will be changed, and I want to find out the new solution of the system. So I have to find out the new equation for the perturbation state. Okay, so if you want to find out new solution, then first find out the equation for the perturbation state. Okay, so now say we had the variable qb. After using the perturbation, it can be qb plus something. So that something, that increment or decrease can be given by this small q. So this quantity is nothing but this is the perturbation which we want to include in our equilibrium solution to find out the main solution. Okay, so after adding this thing, we have to substitute in the equation. So once we substitute in the equation, and if we use the equilibrium solution property, then we can end up with a new differential equation, which is the differential equation for the perturbed quantity, this perturbation q, which is the, so for this q we got this equation, this small dq by dt equals to capital J into q. Okay, so when we are finding this differential equation, what actually we are doing, we are changing the variables. We had the equilibrium state variable, now we have perturbed state variable. That means we are moving from one space to another space. That can be due to translation, due to rotation or something, but we are somewhat transforming from one system to another system. And therefore, you know, whenever we use transformation in a multi-dimension system, then a Jacobian matrix helps us to make the transformation. So same thing here. Here, J is the Jacobian matrix, which gives us how this transformation is happening. And so, actually, the theory tells us dq by dt is nothing but capital J into q. Now, this J is a matrix. You know, this J is a matrix. And later on, we will show that this matrix has a great role in the solution of this differential equation. That means behavior of this solution behavior of this system is completely dependent on the eigenvalues of J. Okay, so if you see the bullet points, you can guess that idea. So here J is the Jacobian matrix. That means you had a system, you are going to another system, so there is a change in variables, and that change of variable is accounted by help of a Jacobian matrix. So it is a say some n cross n matrix, or if it is two dimensional 2 cross 2 matrix, depending on the system of equation, you can get that. Now you know, if you have a very simple differential equation, say dy by dt equals to lambda q, lambda y, then you know that this is a time dependent differential equation. So a trial solution can be guessed in this way using the separation of variable. So using the separation of variable, we can guess the trial solution of this system as q into e power lambda t. That means the solution has an amplitude part, that means which controls the magnitude of the solution, and there is a wave part which controls the behavior of the solution. Okay, so for this kind of system, we can easily find out a trial solution by considering this particular form, q of t equals to some q bar into e power of lambda t. So e power of lambda t gives us the behavior of the solution, how it is traveling with respect to time, and q gives us how the magnitude of the solution is changing with respect to time and space. Okay, so if this is the trial solution, then we have to find out this particular lambda. Okay, once we know this lambda unknown as well as unknown q bar, so q bar and lambda are two new parameter here, and once we know this lambda and q bar, which is satisfying the equation 1, then we can tell that what is the general solution for this system. Okay, so to do that, what we have to do to find out lambda and q bar, we have to substitute this trial solution in the equation 1. So once you substitute this in equation 1, after simplification, you will get a eigenvalue problem. Okay, so what is that eigenvalue problem? That is lambda into q bar equals to capital J into q bar. So why this is an eigenvalue problem? Because here q and lambda both are unknowns, and J is the only known matrix, which is the Jacobian matrix. So just knowing the information of J, we have to find out the value of lambda as well as value of q. And if you remember the characteristic equation for a matrix, you can easily guess that if you take the characteristic equation, this equation is similar to characteristic equation. If you take the determinant value, after taking in one side, if you take the determinant value, this will give you the characteristic equation for the matrix J. Okay, so from the definition of eigenvalue and eigenvector, it is clear that this is a eigenvalue problem, and here lambda is the eigenvalue of J and q bar is the corresponding eigenvector. So once you find the lambda, that means eigenvalue of J, then systematically you have to find out the eigenfunctions corresponding to each lambda, and those are the combination of lambda and q bar which can give you the solution of this system. Once you know lambda and q, put in the trial solution, and then you can find out the general solution of the system. Okay, so this is the idea behind the behind this equation, how to use your linear algebra to solve this simplified differential equation, which can handle some properties of your real life application. Okay, next I want to show you one more example, more general equation, which is much more useful, and you have, all of you maybe have seen this kind of equation, which is called wave equation. Okay, and this is a partial differential equation. Earlier one was ordinary differential equation, and we saw that in the case of a ordinary differential equation, we can apply the linear algebra to solve this equation. Similarly, we can apply linear algebra to solve the partial differential equation also. And so here I will discuss how to solve the partial differential equation using the similar idea. Okay, so this is a one-dimensional wave equation. This is a one-dimensional wave equation, and you can see this is time and space dependent. So u is the unknown variable which is dependent on time t as well as space x. And I have considered, at first I have considered in a bounded domain. This problem I have considered in a bounded domain, and the domain is 0 to 1. Since this is a second order equation, And so to solve this equation, we need at least two boundary conditions, that also given here. So at the boundaries, for any time, the variable u is 0, that is given, and this is the most simple boundary condition. You know, this is the Dirichlet boundary condition. But in certain cases, in certain application, always this kind of boundary condition may not be helpful. In that case, you have to consider some other boundary condition like Neumann boundary condition or Rubin type boundary conditions, so which are mixed type of boundary condition. But whatever may be the boundary condition, if you have two different boundary conditions and if it is a bounded domain, then you can look for the solution of the one-dimensional wave equation. Okay, and same thing later on we can apply for some higher dimensional wave equation also. Okay, and many of you who have already finished partial differential equation or already attended some classes in partial differential equation, they knows that to solve this one-dimensional wave equation, the most helpful technique is separation of variable, and that is easiest way. So same idea I have used here also. Say we are using a separation of variable, and so by the separation of variable, you know that your variable, unknown variable u of xt have to express combination of two different functions. One is function of x and another is function of t. Here I have used the particular type of actually separation of variable, because I want to check for waves. So I want to solve for the possible wave-like solution. So you know, in a wave there is a amplitude and there is a wave path. Okay. So amplitude, how the amplitude is changing, that can be given by u bar of x. That means how the magnitude of the solution is changing. Similarly, if you take the exponential part, which is only function of t, and this will give you the behavior of the solution with respect to time. Okay, first one will give you the magnitude with respect to x, and second one will give you the behavior with respect to time. So this is a particular type of separation of variable. Okay, and this is called normal mode analysis. Okay, so this is basically coming from the idea of separation of variable. So we are taking two different functions and we are separating the variables. Now in this variable separation, there is two unknowns. First one is u bar of x. We have to solve for u bar of x. And second one, what is the value of omega? If we know the value of omega, then we can get the total solution. Okay, so similar like earlier example, our aim is to find out omega value as well as u bar x value. Okay, to find that, again we have to substitute this solution or this actually dummy solution, okay, trial solution or dummy solution in the equation. And you know, in this process we can end up with the ordinary differential equation. If you substitute this in this equation, then we can find out a simple Sturm-Liouville problem. Okay, like say x double prime plus lambda into x equals to 0, or say x double prime minus omega into x equals to 0. So a very simple Sturm-Liouville problem you can end up with if you put this value or this trial solution in the given equation. Okay, and you know how to solve a Sturm-Liouville problem. In the case of Sturm-Liouville problem, you know, we have to find out the eigenvalues and eigenfunction. And since we are interested in a non-zero solution or non-trivial solution, because if you consider any trivial solution, that will not give you the appropriate actually idea, or it cannot be useful for your application. So always we are interested in finding a non-trivial solution, and to find out a non-trivial solution of a Sturm-Liouville problem, you know, you have to find out the eigenvalues as well as the eigenvectors corresponding to the differential equation. Okay, so after using this trial solution, as I told, you can get a equation like u bar double prime, or u and that double that prime, actually you can denote that differentiation with respect to x. So d2 u bar by dx2 equals to something omega into u. Okay, so now if you solve that, you can get just see the bullet point 2, you can get the set of eigenvalues. Okay, so set of eigenvalues means that is the set of values which is satisfying this equation, omega values, set of omega values which is satisfying the resulting stream Liouville problem. So that is given by omega n equals to n pi. Similarly, once you know the eigenvalues, you can find out the eigenvectors corresponding to that system or eigenfunctions, and those eigenfunctions are nothing but un bar, and that can be given by this particular expression. Okay, you can try yourself to solve this very simple stream Liouville problem, and you can verify that if you substitute this trial solution in this equation, then easily you can find out a stream Liouville problem, and the solution of the stream Liouville problem can be obtained if we find out the eigenvalues of the system as well as eigenvectors of the system. But one thing you notice here, that these eigenvalues are discrete. Okay, you can count these eigenvalues, and so omega 1, omega 2 up to omega n number of eigenvalues you are getting, where n is a natural number. And similarly, corresponding to each eigenvalue, you are getting an eigenfunction. Okay. Now, my next thing is, say you are considering an infinite domain, because this problem I have formulated for a finite domain. As I mentioned, x belongs to closed interval 0 to 1. Inside the finite domain, I have formulated this one-dimensional wave equation. Okay. Now, if somebody interested in formulate this problem in an infinite domain, say between 0 to infinity, in that case, again, still you can apply similar kind of method, but after solution you can see that your eigenvalues are no longer discrete. Okay, so in the case of infinite domain, if you solve the one-dimensional wave equation, you can easily find out, or you can easily verify that in that case the eigenvalues are no longer discrete. You can get a continuous spectrum. That means there is a certain region. For each point in that region, each point from that region is an eigenvalue of the system. So this is called a continuous spectrum, and corresponding to continuous spectrum, you can find out a continuous eigenfunction also. Okay, so this is some more insight about the different kind of domain. Now let us again discuss actually how this solution. We have seen two different type of solution in two examples. In first example, we saw that the solution is only dependent on time, and in second, the differential equation has only time derivative in first example, and that is the ordinary differential equation. In second example, we have seen that we have considered a partial differential equation, and the variable is dependent on time and space, and the final solution or the eigenfunctions are dependent on time and space. Okay, therefore we can guess that the solution of a differential equation can change with respect to time as well as space. Sometimes it can change with respect to only time. In some cases, it can change with respect to space only, or in some cases, it can change with respect to both. Okay. So if you see first two figure, you can guess that there is an initial solution. Okay. And then after certain time, the solution behavior has changed, but behavior has not changed anything with respect to the x direction. If you walk towards the positive x direction, you can see similar behavior, like figure A, first figure. But you can see that amplitude has changed. That means magnitude of the solution is changed with respect to time. And due to that, this change, if there is a instability occurring in the system, that kind of instability is called temporal instability. Okay, so in this case, whatever change is coming actually due to the time variation. But if you see figure 3 and figure 4, then you can notice that the behavior of the waves is different here, and the behavior is changing with respect to time as well as space. If you can go from 0 point towards the positive x direction, or if you can choose some higher time limit, you can see that the behavior is changing with respect to both time and space. So similarly, there are some more solutions are there or systems are there where you can see that only solution is changing only on space, not in time. Okay, so there are certain types of actually instability in a differential equation or in the solution of the differential equation. So that I have discussed here. And now once again let me clarify little bit about this perturbation, perturb solution or perturbation or and the equilibrium solution in the viewpoint of fluid flow. Okay, so you can see here I have given two different pictures. In the second picture, you can see there is two different functions. One is u bar of y and another is, and in the first figure you can see another function u of y, which is combination of u bar plus u. So what is the actually significance of these functions? In figure 2, these two functions denote two different solutions. So if you are finding the equilibrium solution, that is given by u bar of y, that means a initial solution kind of thing or a calm solution. So that solution is u bar of y, which is denoted by say the blue line. Okay, and the small u of y is nothing but the perturbation. So your system is perturbed or corrected, your solution is corrected with the certain amount of perturbation which is given by the red line. Okay, so the perturbation or fluctuation amount is given by red line or the function small uy, and the equilibrium solution is given by the blue line or the function capital U bar of y here. But now this is separately I have denoted here. Now if you think about the combined effect, you have an equilibrium solution and then you have introduced a perturbation, then what will happen? The new solution will be combination of both. So variable will be changed as I mentioned earlier. So variable will be completely changed and therefore your function behavior will change, and that function is given by capital U of y. So that is just combination of your equilibrium solution plus perturbation. Okay, so this is the graphical representation of perturbed solution and the equilibrium solution as well as the perturbation. Okay, so anybody want to ask anything till now? Okay, if not, then let me proceed towards the next slide. So in this perturbation theory, I want to give you some more mathematical insight. What is this perturbations? Actually, these perturbations, you can see that a general perturbation can be given by the first figure, and that can be think about combination of different type of wave-like things. And these waves are nothing but, you can think about these are some Fourier modes. Whenever you are considering Fourier expansion of a function, you know you are getting some different modes or some basis function, and behavior of the original function is completely dependent on the basis function. Okay, so graphically I have denoted here the same thing. Say you have the perturbation, general perturbation denoted by the first figure, the blue line, and that perturbation can be think about as the combination of various different functions or solutions, and they are wavelength. So first one is one kind of Fourier mode, and second one another Fourier mode, and like that. So you can add finite number of such, or in some cases infinite number of some such Fourier modes to find out the perturbations. Okay, and further, once you have the perturbation, you can use the Fourier transformation and Laplace transformation both to transform the variables of with respect to time and with respect to space. So if you have a differential equation, say you have a differential equation and you are interested to find out or solve the differential equation and it is very complex, then the first idea is, if it is partial differential equation, complicated partial differential equation, then it is difficult to solve. Now your aim should be to transform the differential equation to ordinary differential equation, because we know that once we have an ordinary differential equation, then we can solve that differential equation very easily. So to do that, what we have to do, we have to use the Fourier transformation as well as Laplace transformation simultaneously in the case of a complex system. And by this process, we can get the transform equation, and if you solve the transformed equation using the normal mode or separation of variable, then it will be much easier. Okay, so that things are mentioned here. So if you have a very complex system, first aim should be to apply normal mode solution, which is nothing but the combination of Fourier transformation and Laplace transformation. So if you use the normal mode solution, which is a separation of variable, but particular type of separation of variable, then you can always transform the PDE, complicated PDE, to the ODE. And you can see here that the solution, the trial solution has two different parts again. First part is amplitude part and second part is the wave part. So this formulation actually for three-dimensional case or with three variables. Earlier we have seen with one variable, two variable. Now here it is three variable, three independent variable. Okay. So in this case, you have a amplitude part which is only dependent on y, and the wave part is dependent on x and t. And now this alpha and omega, they are certain parameters. So if you can find out these parameters and the function phi y, then you can solve the complicated system. And these parameters again nothing but they are eigenvalues for certain matrix. Okay, so that thing I am going to discuss just in next slide, how to construct the matrix for a very complex system after modeling by a differential equation. Okay, so here I have given few few pictures of some systems. Say you have a system between two walls. So first figure, if you see, this is a bounded system or bounded flow. You have a system between two different walls. Hello? Bijoy, are you telling something?
Sorry, it was a mistake.
Okay. Thank you. So in the first figure, you can see you have a bounded domain and or bounded flow. Between two boundaries, you have a flow, and so you can model this flow with some differential equation, and this kind of flow is called bounded flow. In the second picture, you can see there is a boundary below, but there is no upper boundary. So this kind of flow is called semi-bounded flow. Okay, because one-sided it is bounded, there is a boundary, but in the top there is no boundary. So this is a semi-bounded flow. Now, actually, one can ask, say I know the equilibrium solution. So that equilibrium solution actually denoted by capital UY. Here the equilibrium solution for each cases is denoted by capital UY. Okay. So one can ask this question, just say I know the behavior of the equilibrium solution. Is there any method to confirm that depending on the equilibrium solution, my Patak solution will be stable or unstable? And the answer is partially yes, because in certain cases, depending on the behavior of the solution of equilibrium state, you can actually tell about the instability of the Patak state. Okay, so that things are actually discussed in second to actually third and fourth figure. Okay, so I have shown here the solution UY, which are different in two different cases. There is two wall boundaries, and between the wall boundaries you have the solution capital U of Y, and that solution is varying in two different cases differently. Okay, you can see the curvature of this function U of Y is different in two different cases. Therefore, depending on the behavior of the curvature, sometimes you can guess the behavior of the Patak solution. Why? Because you know the curvature can be denoted by or calculated by second derivative of a function. That is well known to you. So once you find out second derivative of the function capital Uy, then you can look for some inflectional point. So inflectional point is nothing but the points where the function actually become second derivative of the function becomes 0. Okay, so if you can find out inflectional point, and that inflectional existence of inflectional point corresponding to a solution is necessary for the instability. So whenever you are interested in tracking instability of a Patak flow, you have to first check that equilibrium solution contains any inflectional point or not. If it contains inflectional point, that means u double prime y equals to 0 in certain points, then there is a possibility of instability in the Patak flow. But that is just the necessary condition, but not sufficient. That means if in some flow system or for some solution, second derivative is 0, that means there is some inflectional point. That cannot always guarantee you that system, Patak system will be unstable. Okay, so some idea you can get based on the equilibrium solution, but not the full idea. Okay, so these are the model problems, complicated model problems, real life problems in fluid dynamics, as well as many applications you can find out this kind of problems. So our aim is to how to model these problems with differential equation and how to solve that differential equation using the eigenvalue, eigenvector knowledge. Okay, so in next class I am going to discuss how to model these problems and what kind of differential equation we need to model this kind of problems, and then again I will discuss how to solve those kind of problems, and towards the end of that second lecture I will give you or show you behavior of eigenvalues and eigenvectors, how actually they are changing graphically, or how they looks like for this kind of particular problems. So all those things I am going to discuss in the second class. So I hope I should stop here for this class. If you have any kind of doubts, then quickly you can ask for this class. After 15 minutes, we can start the next class.
Thank you, Sukhendu. So participants, any doubts? There are no doubts. So this meeting, I'll keep it on. And we'll start next lecture in 15 minutes. Right, Sukhendu?
Yeah, that is fine.
Okay, fine. Thank you, Sukhendu.
Yeah, sure. Thanks.